Okay, I think we are online. Welcome again to this live. It's not a presentation. It's more like a personal tutorial that I'm doing. And yeah, like before, we are going to explain again. Jump a little further with the chipyard stuff, and actually trying to implement it on FPGA. I'm going to do it as open as possible, and the way that we are going to do that is by actually using open source FPGA. So I have two right now at the moment, but I'm going to use this one. This is ULX3 ULX. I don't remember the name quite. ULX3S. Yes, that is this one. Actually purchased it here from Crowd Supply. Yeah, because it has open source tools. Maybe it will be better if we use that. Maybe we can use tools like Yosis or whatever tools we have at the moment for this stuff. If it's proprietary, it doesn't matter. But what I'm going to do is to port whatever we have in the chipyard environment, trying to implement a rocket chip, a rocket microcontroller, for example, that only supports like a machine mode, and that's all. And put inside of the PEA. Now I have more experience with the icebreaker rather than this ULX. Actually, this is the first time I'm going to use this ULX. But if not, it doesn't work. I'm going to try to fit it inside of the icebreaker. But the problem with the icebreaker is that it's so small that maybe the microcontroller is not possible to be inside of all of that. So there's a problem. But we're going to do our best. Well, anyways, we're going to start by going to our project. So let me just put this a little bigger. I think it's okay. So I'm going to put this FPGA here so it doesn't get in the way. Documents, and we are going to go to our stuff that our project was named. I don't remember. Oh wait, no, I don't remember. Oh holy shit, this is embarrassing. Not Linux custom. Wow, I actually don't remember. Should I start over? No. No, we are not going. I think its name is console. No, maybe console. It was console. No, it's not console. Where the hell is? Let's find all the iterations. Type D, and his name is chipyard. This. See if I can find it. Because I don't remember where I put it. Okay, those iterations. RISC-V console. No, I don't remember. Wow. Sorry. I haven't touched this documentation, and as you can see, I am doing this on the way. No, I am not doing this like everything is prepared or something like that. Maybe in a further iteration when I have more time, maybe I can do it with a little more of editing and preparation. Anyways, we have our chipyard implementation there, and all the stuff is there. So the way that chipyard advise you to actually implement their systems is that you modify the chipyard repository. I am against this because Chipyard is constantly developing and importing all that kind of environment that they are doing is going to be a difficult task, and a very difficult one indeed, because they change very rapidly all the hardware implementations, and that is not the way that is supposed to be. So what we are going to do is to try to set up our repository and make Chipyard more like a what is the name it more like a dependency or a library rather. So I am going to go to my GitHub. I'm going to create my own my own project. So obviously I'm going to sign in. So I'm going to create a new repository that is named just like we named it before, RISC-V console, and attempt to do a RISC-V console. Just an attempt. And we are going to create our repository, and we are going to create it here also. So get init. We're going to add a touch .git models. I don't quite remember how do we do that actually. How is the this stuff? So we have RISC-V is a thing. We have RISC-V test. We shall organize this maybe in KDR software, and KDR hardware, MV Chipyard to hardware, MV RISC-V is a sim to software, and MV RISC-V test to software. Okay. Now we are here. I'm pretty sure that Chipyard has also the RISC-V sim and the RISC-V test, but because we are doing this in this tutorial, we are going to do it from scratch. For now, the only thing that we are interested in the inside of the Chipyard is just the hardware. So it's going to be like that. So I have here the document. I'm going to I use Gedit. I don't use Vim. For me, it's too problematic to use Vim. I know that you can torture yourself actually doing the stuff. I know that the people can do very much things with Vim, but I personally don't like it. It's a shame, it's a shame because it's supposed to improve my stuff, but I already tried it so many times. And still doesn't stick with me. I am still with the people that clicks a lot and don't type too much. I wonder why involved in programming if I like this. Let's not dig about that. I'm going to copy the git ignore also, the git modes and the git ignore. And the reason because of that, I only need like a template to add our project, so something like this. So I need to put a hardware Chipyard here, and this project is named Chipyard, and the URL for Chipyard, if I'm not mistaken, is UC bar Chipyard. Then we copy, then we paste several times to make it to RISC-V SSM. So this is in software SSM. This is for avoiding to actually add the models all over again. Is quite problematic at least for me. I if I'm not mistaken, this is RISC-V. Let me confirm if this is the URL for this one. Yes, it's okay. Same for the other one. Actually, we can just copy this one and paste it here. RISC-V test. Yeah, RISC-V tests. Put this here, put this there, put this here, and we are go to go. I'm going to confirm that this is the address for the other one, so we don't screw it up. It's okay. Perfect. Did add a new status. Yeah, we know that it is embedded. Let's see if we screw it up. No, gain nor, gain models, get tests. We have modified things on this right test. Let me see what is there. Get status. And get this configure. What the hell? Ah, maybe because of the auto config that maybe I run here. That's okay, doesn't matter. Commit and first initial commit, like always. Push region master. Get remote add origin and this bullshit here. Perfect. We have our project, this initial project, up and running. This is cool. So from now on, we are going to try to first create this project in a SBT manner. The way that the chipyard works is that it will execute what the SBT with several projects that are inside of the chipyard itself, and that's pretty much it. From there, it just executes maybe some things more for the simulator and that kind of stuff. But for now, we are going to focus on creating our own hardware environment using chipyard as an aid. So we are going to do that. So first of all, for just taking things here a little borrowed, I'm going to borrow the build.sbt. I'm going to borrow also the project folder. Actually, we only need build properties and plugins SBT from here. But we are going to take everything. What else do we need? We need the variables, MK, chipyard, and also we need the command for MK. And this is pretty much what we need to modify. It's going to be a little heavy for the people that is not used to SBT, but what I am going to basically do is to create my own project using the rest of the projects as the definitions that they are. So I'm going to start that by using build.sbt as the first one. So this, let me color it. This is Scala actually. This works like in this way. It creates this shipyard root, and this shipyard root will be the common settings for all, and it assumes that the shipyard is the only one that exists. So we are not going to do that, obviously. We're going to put here anything else that is not shipyard root. Shipyard root only is used this and here. So I will use this as our stuff. So console root, I'm going to name it console root, and the console root is here. Everything that is in directories, we need to move it also to the shipyard. So rocket ship right now is not in generators rocket ship, it's in hardware shipyard generators or shipyard generators rocket ship. And what we are doing here is just making everything suitable for us. So this FireSim, we are not going to use FireSim. We don't have Amazon, the Amazon FPGA. That I don't know what it is. I don't ask me. I am as clueless as you when they talk about FireSim. There's some seems to be like an internal UCB thing there. But if we need this FireSim, if anything, we're going to default it to put it as a library by default. So we're going to put it here. And we don't need this because yeah, everything is going to be like not going to use. We're going to use the internal version of the FireSim if it needs FireSim. Now this about Maven. This thing about Maven is for using the Maven repository, like don't load it from the source. So we can do that, but we can rather actually ignore it and just use the one that is in the repository. So we are going to practically use this always with project dependency. And that's all. We are not going to use this at all. And this fresh project, actually, this was a good idea that they had to actually make the projects actually sub-projects of another thing when the dependencies definitely doesn't match, because the dependencies are totally a mess in this conglomerate of projects. Isolate all tests. I don't see why we need to use it. No, we can just ignore it because we are not going to use FireSim at all. And it is only used for the FireSim. So bye bye. Also you, bye bye. I hate you. Oh, okay. So chisel. Remember, everything is inside shipyard. Same for the FireSim that I also forget it. Chisel is inside shipyard tools. Chisel inside tools FireTL, inside tools Triddle, inside tools, and you get the idea. So this is not a fancy way to do it, but it's a way that works. Project in Rocket Chip have load macros and the API config chip alliance. Fresh project in Rocket Chip. Okay, this one. From here is this one. Generators shipyard, generators tracegen, generators utils, generators IceNet, generators Hatcha, generators boom, generators Arian, generators 3, generators Gemini, generators assembly DA, two bar tools tape out, bar tools Scala Lab, bar tools macros, bar tools DS tools, Barkov's DSP tools for Rocket, sci-fi blocks, and sci-fi cache. Yes, and now we are going to create our own stuff here. So we are going to name it lazy ball RISC-V console. And this is going to be the projecting file about this with the common settings. Actually, about the common settings, we haven't changed this. We don't have to change it, but I am not representing the USC Berkeley, so I'm going to name it whatever I want. So github.com. Okay, dude. I don't know how this works. They don't teach that in anywhere. You need to be in a very professional environment to name this kind of things. Version obviously is 0.1, and that's pretty much it. I'm going to check the live a little, if the live feed is okay. Yeah, the live feed is okay. Okay, continue. Data blah 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 blah. Okay, so we are going to do this project in file. So right now we are going to save it in another in hardware RISC-V console, and we are going to put everything about our constructor for hardware inside here. RISC-V console. Depends of actually it depends of a lot of things. So rocket chip, shipyard, chisel, and whatever we have there. Maybe the tape out also. Maybe the utilities also. Yeah, I think we need to make it depending on the utilities. It depends of whatever we need. Maybe we shall use the boom sometime, like the Ariane as well. We think we are good to go, I think. And those are totally necessary. We don't need to compile the FireSim, but we need its libraries, because there's a particular one that we have here, that is the HI3, that they have only one dependency that is inside there and doesn't let anything compile. I know it's a little buggy, but it's development, so I don't care. We don't care. So this has a pretty much project stuff here going on. We can put our this shipyard configuration here. We can add our own as well, but we are going to default to our stuff. So the subproject is going to be the RISC-V console, and right now we are going to add one step here for our project for the console. So SVT project. The SVT project is whatever we name it here. So it needs to be named exactly like this. The model is still we have still no model. So this is the on change. So we are going to practically generate the same things as the default shipyard for now. We need to create a bare bones project. We need to create a bare bones project. We're going to base it on the shipyard. So I am going to create. I'm going to hardware. I'm going to take to create this RISC-V console. Is name it like this? I name it like that in the RISC-V console. Yes. So RISC-V console. For this, we need to create what? We need to create SRC main Scala. So I'm going to parent it main Scala. Then we need a build.sbt as well here. Torch build.sbt. Sorry, we need to edit it. So we are going to actually modify. We are going to use the chipjar SBT. They don't have SBT here. They only have the SRCs. Okay. Maybe we don't need the SBT here. But I'm going to keep it if anything happens. But yes, pretty much we created our own project, and we are ready to go. So based there, everything is based around this thing here. The base there is not defined in variables. I wonder why. Regardless, is not generators rocket chip, is hardware generators. Our chipjar, chipjar generators rocket chip. So we need to take care about this. Build there is okay. Everything that is named from the base there is the one that we need to take care of. The same there is okay because it's a simulation directory. I think we are good to go around this one. The variables only needed to be modified in that way. Not common. Common, it has more things, so we need to take everything that is named from base there. There's a good starter. If we screw it up, it doesn't matter actually. It doesn't matter too much. I mean, now this needs to be here. And now I remember that I need to create a library. This is for making a VRTL like a compiler library, and it gets recognized by the whole Java environment, maybe, or is the Scala environment? Not sure. Also, so this is for creating for the utilities. The utilities are not there. It's here. They are here. And I created this one here. CD to base there. No, this needs to be executed here. Project, the SBT project, and go to the generator. Okay. What else? Chipjar. The project type out. Then generate the top and harness. Okay. Parse tools, macros for the macro compiler, and this for the DRAM simulator. We are good to go. And right now we are going to take the simulator as the base as the base subject for creating the Verilog files. But we remember that we are going to implement this in FPGA, so we are going to create another folder that is named FPGA. That we are going to create this FPGA there. We are going to name it this the name of that thing, the ULX 3S. So as long as I'm aware, they have here in the chip here a way to do it in simulation. So we are going to copy the simulation utility that they have. For example, this makefile. I think that is the most necessary thing here. Everything else is not necessary, I think. CP. Oh, sorry, ULX. CP this to makefile. I want to copy here. It's ready. It is makefile. Okay. So this, in conclusion, will take the Verilog and we'll try to compile it to a very later stage. That is the executable that does the simulation. But we are only interested in the Verilog files. So the base there is defined here, and everything gets included in the base of the base there. So the base there needs to be our project, and Chipyard, because it was the base project before, it takes the base project as it is. It's a little complicated and this is a little hackish, but I think it's the good way to go if you need to use the Chipyard just as a library for that regard. So yeah, they need the validator here, but we don't need it. Include a share file. So yes, this thing. The sim name is validator. We are going to name it ULX3S, if anything. Prefix simulator to the sim there. Where's the sim there? It's here. And the sim debug is going to be here, but we are not going to create executable, so this is going to go here. The sim prefix is used anywhere else? No. I'm not going to use this. So the default is the sim and the debug is the sim simulator. We don't need to take this, but we rather should go. But this doesn't get used anymore also. But we need a basic problem, a basic program, a basic rule to make the Verilog file. So we are going to keep this default here, but I still don't know what to do here as a target. Then we include the common. Then this is the very later stuff. The very later stuff is everything here. We don't need it too much. What about the sim? It needs the model MK and the DRAM sim lib. And the model MK will remember that validator creates a series of C files and a makefile. So that's what it needs to create the Verilog MK file. So we don't need any of this, and the only exact thing one we need is the model MK dependencies. There you go. So there's the sim CRCs that they are not defined anymore. It's the sim common files and the extra sim requirements, and we don't have here also. Those were before this extra sim requirements. Nope. Let's restart the whole thing. I'm going to revert if anything. No. They are maybe an optional variable. And the sim common files. And what about validator operate options? Sim BRC. We need the value of BCM series. We need the value of this. We need it somewhere else. Where's defined? Maybe I screwed it up. I deleted them. Bin sim BCRCs 3, 2, 1. It's not defined here. Maybe it's defined in the variables domain K. Yes, top file and the harness file. Okay. It's defined here. So we can just refer whatever, and we don't need any of this. Actually, we don't need anything. And we can just call it a day and clean whatever we need to clean in the generator there. What about the gender? It's not defined anywhere. I think it's defined in the variables. You need to be in the same there, and the generator is RC. Okay, perfect. So we actually ended up with a very simple makefile. So we include this variables domain K, and we do the default, and the default rule will be the same BPSRCs. By the way, I haven't extracted yet this one. So this is that is the rule that we're going to follow. So when I execute this makefile, it will create all the Verilog files inside of the ULX 3S folder generated SRC. So all the Verilog files that are needed for compilation are inside there. It's very exciting. We can just put it there and make it and try to make the makefile and see which problems they have, but they will arise. So this is the stuff. Make default. Let's try it. Right now it's doing some things. Okay, the FreeRTL is already compiled, so it only copied it. So I have a problem with my build SPT because this Arian is not typed with double N. Maybe yes, it's not double N. It's only single N. Retry. By the way, the new version of Chager that is being developed is not going to be this easy. they have a more complex dependency tree. Okay, we have repeated stuff here. So because we put the sim build maybe from the Firesim or the Midas. No, the Midas project was this one. We don't need this. You can go away because some of them because they need the chip year as a dependency. It gets loaded twice. So it tries to make the chip year as because the chip year is supposed to be the main project. Same problem again. So it was not Firesim nor Midas. Or maybe we can just restart. Or maybe it's the Midas target utils. I know that is the Midas target utils. I have a hack for this, but I need to. The resource for this is in another project that I have here that I cannot show. So I'm going to just copy it because I don't want to exploit myself to actually trying to investigate it here for you. So I actually loaded this like instead of a project ref, I loaded like a project in file. Okay. So instead of using this Midas target utils as a project ref, I'm going to use it as a project in file. So hardware chip year sims Firesim and Midas target utils. Perfect. This is used in hardware float and in C#tree. This is supposed to be all. maybe, but we are going to restart, so we are going to just abandon this, quit, and we're going to do it again. Let's see if I have it. Let's see if I have it. Okay, it did not load for anything besides outside there, so we are good to go. I wonder if Chipia got updated recently, because this is not normal. github.com/this bar Chipia. Oh, okay. December 3. What about the latest one? 24 days ago. It's not that far away, but I don't remember being. I don't know. But they are prompt to. Anyway, this is compiling the whole stuff. Right now we don't have any sources, but that is okay. We intend to include sources to create our own sources afterwards. And I repeat again, I don't have anything prepared for the ULX yet, but we are going to create the first glance about creating our own configurations and stuff to create the microcontroller that we want to create. It's going to be a simple microcontroller. I think maybe just a new art, and some GPIOs. Maybe that's okay. Maybe a little SPI. I don't know. We can put an SPI because this ULX, I see that they have a SD card reader, so we can put the SD boot and boot from there, or we can do it with the QSPI. Let me see if they have QSPI here. I think they not. Oh, they have a Winbond, a 25Q128. So we can use either, or we can save or part of the stuff there. Okay, we have a problem here. Class not found. That it was generator. The problem was because when it created this without generators. So whatever is here, project here. This is in the common. This problem is in the common.mk. So, for example, what happened is that when it tries to put all of this, it did not create anything. And I think I know the reason. Variables. We have variables here, and the RISC-V console is not here. Yes, I didn't put a case for the RISC-V console. Sorry, my bad. So let's do it again. Okay, now it's going to create, and now we know that it's going to work because it has the names. So if anything else happens, it's maybe because I forgot to put anything else that is not there, and now it's compiling a lot of bullshit. This is looking good. This is looking very good, actually. Now, as you can see, Chipia is a collection of hardware hardware libraries. And because they are hardware libraries, we managed to do it inside of this build as SPT that we modified from the original. But we are using this as our own project. And this project that we have here, the RISC-V console, we can use that to create our tops or reference anything that we need for rather rocket chip, shapeyard, chisel, utilities boom, or anything. Actually, I think we shall need the sci-fi blocks and the sci-fi cache. I know that we need sci-fi blocks because of the GPIO and the UART. I mean, they are pretty much used a lot, so we can use them. We can create our own, but let's be real. The drivers won't exist unless you create it by scratch. Maybe you have a legal issue. We can jump into that. Okay, we have a problem here. It says here the RISC-V console.generator does not exist. And we can fix that pretty easily. So the problem is that the way that the generator works, it tries to treat any of the project as the main generator. So it has to have a generator, but we can supersede that generator to another stage. So we are just going to make an Scala file that actually just supersedes or makes a dependency of the other one. Nothing too much. Let me describe you how it's done. So RISC-V console SRC main Scala. So we need to create our first Scala file here. So I'm going to make here a generator folder. Then I'm going to copy actually it's a lot of levels from chipyard generators. The chipyard one, it has to have a generator here. So just Scala, the generator is here, and we are going to copy here generator. And as you can see, the only thing that they do is to call this stage main chipyard stage. So right now we are a step inside of this. So this project is named according to the variables. The SVT project is named RISC-V console. So we shall name it the same way. Or you can rather modify this to actually make it work for your necessities or my necessities. But I think this is a little more in depth, because we can see that what we actually have here is just software doing hardware. This is a good example about this. So we need to import chipyard to using chipyard stage, and the generator that we are going to use is chipyard stage. That's pretty much it. We did not do anything else. Actually, I think we don't need this import, but let's see. Let's go again. By the way, this simulator I did not use the generation file for some reason. I need to look into that. RISC-V console text harness. Okay, I know what is happening. We are going to look at this all the time. No, we are not going to do that. We are going to do it in chipyard. We are going to create on for now the chipyard. The config pages is chipyard as well. It's okay. Let's do it again. Yeah, because it's trying to search for a RISC-V console test harness. That doesn't exist. We haven't created. We are going to just use the chipyard one. And because our project is based on chipyard, it will find it. Because everything is inside of the same jar file. And pretty much works. That's good. No such file or directory because boot room doesn't exist. Okay, but we don't need anything more else. This is good enough. Let me tell you why. The reason is that the boot room that is trying to import comes from the boot room utility, and that boot room utility has their own boot room images that are already pre-built. But you can understand how this works and how it is made and all the stuff, but it won't give you in-depth of what is happening in the hardware. So right now I'm going to leave it like this. So if this file exists, it will create the Verilog files. So trust me on this one, the Verilog files will be created. But right now, because this already happens, this means that the processor is being made. I mean, from chisel to FreeRTL. From there, it's just the FreeRTL to Verilog and the macro generation. So pretty much we are almost good to go. That is a good thing because we already have everything now ready to go. Up to now, we have our project ready, everything ported to our stuff. It took us 1 hour to do it. I mean, it's not easy to do, but it's not recklessly difficult as well. And now we can just insert whatever we need for our necessities to create the microcontroller. So we are going to do that, but before that, because we already know that this compiles, we can use finally IntelliJ IDEA, and you are going to love this because it makes it so easy to do. So easy to import projects here. So we are going to import the RISC-V console. Wait, maybe I did it wrong. No, I'm going to do it with the open utility rather. So this is the RISC-V console. We need we need to use the SBT shell for imports and for builds, whatever project GTK you have, and the general settings, the GRE, whatever you have. And for now, the launcher, let's go to do it bundled. We can use the custom one that is inside of the Rocket chip. But the bundle is okay. the folder project is empty. Yeah, I want to overwrite it. It's okay. Thank you very much. And I will start to import the stuff. We can up to this point import everything out. Push everything. View status. Let's see if I got it right. View status. Let's see why I'm pushing. This is okay. Perfect. Git push. Git commit. Perfect. Now we have more things in our thing. Very good. This is looking good. So right now it realizes that actually got inside and is indexing all the stuff. From this point on, we can use this ID to actually create the stuff. So we can go to, for example, software. No. No, hardware. Sorry. Verify console SIC main Scala. The generator is here. So we can create our own stuff here. So I'm going to create my package here that is named RISC-V console. And this is where we are going to put our stuff. So first of all, this how to explain this? I think we need to create a drawing for this because it's a little difficult to understand for the first glance. So I don't know, live behavior explanation. Actually, it's not behavior, it's a rocket jet. So in order to personalize your environment, you need to first understand the environment, but I'm going to give you the tour of what is inside. So you need to stop thinking about the chip here as a HDL. You need to stop thinking about that. What you have in Chivier is a bunch of software that will create the hardware and exploits the whole software thing of the Scala to actually make it work in a supersede manner. So to explain this, we need to understand this concept about lazy model. The lazy model is just a construction that will initialize variables prior in a lazy manner for creating the model itself. Usually is named non-model implementation. So the true model that you are used to in Chisel is going to be inside of a variable named model inside of the lazy model. And as we will go on, you will appreciate that this model is this variable is lazy. That means when you generate a module inside of a lazy model, it will initialize all the variables inside of the lazy model, Then we'll create the model with any of the variables that you put inside of, because yeah, this can be these variables can be anything. So they have actually a diplomatic thing. They call it diplomacy. That is dependent of the lazy model, and the diplomacy will handle whatever nodes are in. There are the buses or the interrupts or whatever it needs to be constructed before you construct the hardware. So you need to understand very well what is actually hardware and what is going to be constructions for generating the future hardware. So this is why in nodes the nodes gets a little confusing, because you think that the nodes are a hardware, and they are in some to an extent. But what you don't know is that the nodes will actually just carry like information of whatever node you are creating, and when everything is set up, it will finally instantiate the module itself with all the ports that it needs and all the stuff that it has. So that's how it works for Rocket Chip. The reason why I know the reason, and the reason is that to avoid using dangling functions. For example, when you have your buses created, you need to create a final function that actually create the hardware. That also works, but it's not going to be scalable. And that is the whole thing about Scala, that the software gets scalable. In this case, the software about getting hardware created. So that's how it works for the whole thing. So they have from this lazy model, they will create another basin of this one. This is the base one. That is the I think it's named Bear system. Now we'll only create the DTS, the DTS and the DTS and JSONs maybe. I don't quite remember. We can, if we are right there, we can explore what is there. And remember, this has also a module implementation. Right now, because it's just the DTS and the JSON, the module is empty, so it doesn't have anything there. From there, it will instantiate, as long as I'm aware. I think the next one is the base model, the base system. So the base system will have what is risky about this hardware, because it will create all the buses, the main buses. So the main buses, remember, the buses are nothing else than other lazy models, and lazy models get instantiated inside of lazy models. So it's okay. They are going to be in the context of a lazy environment. So they have all the interconnectors. So they have they name it TLX bar. They have a lot of them, namely the S bus, the M bus, the B bus, the C bus. What else they have? Yeah, I think it's like that. And the way that they connected it is actually configurable. Before there was not configurable. It was like the system bus is the main one that connects to the processors. Then from the system bus we'll create the M bus, the P bus, and the C bus. I think the C bus comes first, and the latest one is the P bus. and everything gets instantiated using this TLX bar, and that TLX bar is a node that uses a lazy module that later will create the bus itself. That, depending of all the interconnections that they have, it will decide if the tiling that will connect is the full version, the one that has the five channels, or if it's not needed according to the parameters, it will shrink it to the two channel version one. Normally, the system bus is the one that actually carries all the five channels, the A, B, C, D, E. But the next from there, the M bus, the P bus, the C bus, they are configured to be smaller, but all of the same. All are tilinks X bars. It will create this. It will create also the interrupts. The interrupts. The interrupt node. I think it's named node, and this is an int bar. I think, or is it an int something? I don't remember. And that's basically it. Sometimes I don't remember because of the version. They will have also the plague and the clint totally instantiated here. So as you can see here, you see that if you are going to implement a rocket chip, these two modules are totally mandatory. So they need to be there. And also in some instances, even the debug is totally mandatory. So those three are totally mandatory for actually handling the whole stuff. The reason is that they have actually this in node here, and the in node is totally controlled by the PLIC, that the PLIC will deliver the respective machine interrupts to the different cores. So the PLIC needs to be controlled. So the philosophy of the RISC-V is that the interrupt controller is not inside of the processor. So all the interrupts doesn't arrive to each processor. Actually, all comes inside of the PLIC, and the PLIC will reroute them to the respective cores. The clint is the one that actually supports. So the PLIC is the one that controls the MIP. Now the SIP. The SIP, that is the software interrupt. This is mainly used for multi-core processors, but it can be used also in one-core processors. And basically what it does is one core that will interrupt another. For example, for making a core enter another core in supervised mode, or you want that core will handle another process that you previously write the address of interruption before. So, for example, if you want to do a multi-core process, you will interrupt the other core in machine mode or in whatever mode that you are in to actually make it work in that process specifically. So that's the way that they do maybe threads, if you want to see it like that. The debug it basically handles the debug interrupt. But as for the debug interrupt, it's not a special type of interrupt that is optional, but it's kind of mandatory in all the systems that you want to debug. So it will just provide the debug interrupts depending on the debug model. Pretty much is it. And we have the time interrupt that is actually controlled again for the client. So the client actually doesn't only handles the what the doesn't handle the only the software interrupts, but also the time interrupts. So for example, you can program a core to actually execute certain thread during certain time. That is good for the scheduling, and this is mainly made for the Linux environment. So for example, if you are doing a multi-process and you have a process in user mode that is executing, and you want that process to only be executed during 1 millisecond. So you program the client to actually make it 1 millisecond, and so on. So that's the whole paranoia about this basis system. It will just create this. So it's not that difficult. I mean, if you dig up deep enough, you will see that it's actually structured like that. So from the base system, they actually created sorry, this is base subsystem. Sorry for this. Base subsystem. And the base system is supposed to be the system that actually implements whatever is more necessary. For this regard, they implement these ones. I mean, they implement the hardware version of this one, the hardware, like the actual thing that is going to be controlled. This only is for making the interruption buses, if you want to see it like that. But the actual hardware is going to be created here. But you need to make the base system actually have the client and the back in order to everything to work, because otherwise it won't work. At least in my perspective. You can modify it a little more, but it's going to be a mess. So so this is only the environment for this to work, and the base system will have the actual hardware to work. From here, you can see afterwards what chipyard does, or in this case also rocket chip. The rocket chip finally implements a system here that is named literally only system for the rocket chip. That doesn't have anything, but for example, it has the chipyard system that will instantiate the whole processor thing. So the system in rocket chip only has the instantiation of the cores, of the rocket core in particular. The chipyard system, in the other hand, it has the instantiation of the rocket and the boom and the Ariane and the Hacha as well. So we can do that. So in order to do this microcontroller, we are going to use this base system as our system. From there, we can use maybe the chipyard system to create our processors, but we can implement our processors if we want. So we can use whatever. But in order to understand it a little in deep, we are going to use the basis system, and we are going to implement our the rocket core manually using our system instead of using chipyards. But it's going to be basically the same code, so don't worry too much about it. From here, we can supersede a little more. They have a little more here. That is the whole system. Then from the whole system, you create your platform, and that is the way that is organized. So we are going to do that practically. So we are going to create a new file here that is named RISC-V. I'm going to name it from now on RBC. RBC system, that we are going to create our own system based on the base system. So we need a package RISC-V console that maybe system, I don't know, something like that. And we need to import a lot of things. So import chisel 3 obviously. Import chisel 3.util in the utils. And we need a lot of things from the free chips project, the rocket chip, but I don't have it at the moment. So what I'm going to do is, because I always take inspiration from the other projects, I'm going to go to the chipyard project and actually copy from there. They have a system here, and the system only has this, but we don't need it. We need the subsystem. The subsystem is the one that, as you can see, instantiates the cores. So actually we screw it up, and we shall create first our subsystem. So we're going to create our subsystem from now on. Subsystem is without yes and uppercase. I'm just trying to mimic the style of this people here. I don't know what I'm doing. Okay. So as you can see, we can do this trait here. They have a trait here to actually do this. We can do the subsystem with chipyard tiles. Okay. But we basically need this too. And the good thing about using IDEA is that it will auto detect you whatever you need to import. So it will just put it there all the way around. That is useful. And we are going to avoid actually using a lot of these things. We are going to just put it with underscore all the things that we need. The elaboration artifacts, and well, the dramatic helper is a little there. So we are going to try to not depend of the chipyard. So we are going to just keep it here. So chipyard tiles doesn't exist, but we are not going to do chipyard tiles. We are going to do our own tiles. For that, we are going to create our trait here. You guys create it there, then we can put it here. Has RBC tiles, no? And we need an implementation for this one that only has this. Okay, as for now, we are just copying and pasting. Yes, don't worry too much about it. Don't worry too much about it. We're just doing our stuff. To the back model implementation, and we are go to go. We'll put it here. Perfect. Oh wait, we have one error here. It's expecting this. The model, what is needed is because we are not using the same one here. And again, I haven't okay, I don't need this one. Subsystem, it must declare abstract. It was declared abstract before? No, we need to define something that is not defined yet, or we need the member in core monitor bundles. We need to make it. We need to declare it. Perfect. We don't need anything else. So we are finally here. Let me see. Let me brief you what is happening right now. So then again, I'm going to bring this particular thing again. Fucking this thing here. We have always a lazy module and a module implementation, but it's a little deceiving, as you can see. For every trait or for every class or for every abstract class that you create, you need to create actually two. One for the perspective of the lazy module, and other one for the module itself. That's why one is named the true name that is named, for example, has RBC tiles, and the other one is has RBC tiles mode implementation. So you need to use this one with module and this one with the lazy module. As you can see, maybe this will require that maybe some of them use the, for example, the versus system or the basis system or the versus system, and finally it will go finally to the lazy module. So you know that this always needs to be a lazy module. In the other case, for example, for the module implementation, for the in this case the debug, it implements a lazy module implementation, and you know that lazy module implementation is going to be a module. This is a module. It's a multi-IO module, but it's a module nevertheless. So that's the way that is done. So we need to start. Actually instantiating the course. We can do it in the same fashion that Chivyard does, but we're like always, I'm going to explain you how this works. We need to have the we have to need the model instantiated. No, cancel. This needs to be created. Then we are going to just implement the rocket tiles. So this will have the rocket tile params. The rocket tile params are nothing else but the parameters of the core that we need to create. This comes from the configuration deck. So we will get the actual variable from here. We are not going to instantiate any of this. It seems to be we need to create this variable for some reason. I also don't understand. Sorry. I also don't understand, but are the crossing? I assume that is the crossings for the the crossing. What is the crossing? Maybe for clock crossing. It has a lot of clock stuff actually going on. So that's why I am not going to dig deep into this, but understand that they have a reason to be there. And finally the tiles. So we can it will sort the hard ID, and we can call each one of the tiles. So we are going to just copy this and paste it, and we are going to just leave the rocket tile parameters there. We need this is imported, so I'm going to import it. Same for the rocket tile, and this time is obviously necessary for some reason. And now the final the function that makes that this error appears, it needs that this function here, that is the core monitor, needs to be defined. And because right now is defined, the system works. Good to go. We have our subsystem. Let me brief you again. Maybe it's not clear. For the people that maybe don't understand what is a trait is just something that you can add to a class later. So this will be added to the class. It assumes that the class that is based on will be something that is based on the base subsystem. So whatever is attached with this RBC tiles needs to be extended in base subsystem in some way. That is what it means, this thing. And we are expecting that this variable module is the type, it has at least a type that is extended to this thing, to this module implementation. So we are expecting that the module it has these variables here. That actually we don't have anything here. That is so that is cool. So we gather the rocket type params. We create the rocket crossings. I think they are clock crossings. Not sure. Don't hit me if I am wrong. Don't hit me if I'm wrong, because no idea. Then I use the old tile info, because the old tile info is the one. And we actually only have the rockets, so whatever. If we plan to put more cores, we can put it there. Then we sort the tiles by the hard ID. And we run a map, so there is a for with a return. So whatever it's in tiles is whatever it puts in the last thing here. So every about the tiles info will have the param, that is this thing, which each one of them, and the crossing that we have this thing. So if the param it matches the rocket tile, it creates the rocket tile. It's instantiated, nothing else. Then connects the master bus, the slave buses, and the interrupts, and returns the tile itself. So there is going to be the actual representation of the tile in lazy model. So the core is not actually generated yet. It will be generated in the context of the model, this one. But this is enough for actually just creating the model. This is like a request. Yeah, we are requesting very kindly to the rocket generator that please instantiate us a rocket model, rocket to a lazy model. That will create the model. You already get the idea. Then this is for the core monitors. Because of the structure of how is made the rocket for now, it needs a core monitor, and it's there. It will take the core monitor. That's all. I am not going to get anything else there. I don't know what is the core monitor used for, and we don't need it. We only need that the processor actually executes our instructions. That's all. Nothing else, nothing more. So that's pretty much it for the submodel. So the subsystem will have the base subsystem that, remember, that is needed to be extended, and the RBC tiles that we just created a little app. And this one we have the subsystem, the bare subsystem for the module, the reset, and the RB tile. So as you can see, the module is here, no? And it's ready. That's all for the subsystem. Now the system is going to be a little easier, because we only need to create our two stuff. So class RBC system extends RBC subsystem. I think we need to include this. I think I put it in a, no, it's the same package. Sorry, I name it subsystem only, RBC, and the RBC subsystem. Once again, it will highlight whatever it needs to be corrected. So it's okay right now, and right now it's here. We need always to have the implicit parameters. This is for traveling the parameter stuff during the whole thing. It's implicit, so it will always be used if the context is provided. Same for the other class. This needs to be the same way that we actually did it this way. I actually don't remember how it is, so we are going to just copy and paste it. So the RBC system module that we're going to create, that is based on the RBC subsystem, will be an extension of the one that we did before. I wonder if people is seeing the text here. I mean, maybe the editor is a little. Sorry, it was like this a long time ago. I actually did not pay attention to the font. I am so sorry. Let me go with 14. 14 is okay. Let's compare with this thing. I think 16 is good in order. No, 14 is okay. Now it feels a little uncomfortable. So as the same, you need to override the model, because the model that you need to actually create is your model, not the subsystem one. And we need that this outer, the outer is already here, so it's okay. And the outer, I put it here, so we have access to the outer. So let me preview. If you want to access things from the module, you use the module, but you usually in this context don't use the module, because if you access anything inside of the module, it will create the module. So it breaks the philosophy about pre-initializing the parameters for the hardware that you need to do. So you rather not use the modules here, the module stuff here. But in this case, when you are inside of the module, you can access the outer. And the outer, we have all the nodes or the parameters that you put inside of the lazy module. So that is the way that you can communicate both of them. But for now, we are just going. We are not going to do anything fancy. That will be relevant after. but we will put inside here the stuff that we want to put. So for example, the GPIO, so the RISC-V with GPIO, maybe GPIO something, GPIO pins, GPIO something, GPIO, I don't know. We need to see. No, this is the register router. No. This is not the way that it's done. The GPIO periphery has periphery GPIO. Okay. Remember, the trait is just something that you add at a base class. So we are adding this to a base class. Get it? And it has periphery UART. And remember that we also need if it has it, the module implementation of each one of them in the respective module. And that's pretty much it. From now on, both the GPIO and the UART will be created inside of the project. This is good. So we don't have anything else. We can add the optional stuff and maybe create the rocket core and all the stuff. But for now, we are going to leave it here, I think, because I'm a little tired. I mean, we can put a little more, but I'm afraid that will be long enough this session. Let's do it a little more. We're just going to create the slave AXI port, the main port, actually the master main port. This is for creating an AXI4 master. They have an implementation? No, they don't have it. And we are not going to use the boot room. We are going to use another thing. So the boot room, yes, the boot room is a problem. I don't like to use the boot room because it will always try to get the .img right into my face, and I hate it. Instead of that, we are going to use the max room. That is a little different. It's a little different in the regard that you can just put whatever inside of your max room. That is why it's named. It's a masker ROM, and you can put whatever ROM that you want there. It will be created inside of a configuration file and everything. Then you can just put whatever program that you want there. And the master, why this is important? The boot room, as it states, is the boot room. So the processors will reset at the address of that boot room. It will start to execute instructions from there and jump from there to whatever it needs to jump. So if you want to have your own boot room inside of here, you can put whatever you want. Usually they put in the boot room, they put something like jump to the RAM, for example, or jump to whatever. In the case of this boot room, I am against this boot room because the boot room will wait the WFI until another programmable stuff actually tells them to jump where it's supposed to jump. So it's a trap. It's a trap where it's totally looping itself, doing anything. And you don't want that for your system. At least I don't want that for my console. I don't want to connect a JTAG and via JTAG actually command the instruction to actually do it. You can change the image file, but then again, I think you will have more control using maxrom. And we can override the subsystem RISC vector if we just assign this global vector before. So let's do that right now. The global vector, the global RISC vector is going to be I know this a lot of people is going to hit me because of this. Let's put it here, 0x then .u. And this is the vector and this is the place that the processor will be executing once I put it there. But I need to create my maxrom first. So they have here an attach, and this is a little of a problem. It's a little problematic because you need to understand how this works. So you need to have your maxrom parameters. So the only way to get your maxrom parameters is to actually get them. So again, anything parameters related is inside of the lazy model. So maxrom parameters is equal to here. Nothing special. Maxrom param will be p of maxrom key, very small key. And this is not defined by default, so we need to work from here. So we need to import this maxrom library, that is this package here. And we can import it finally. Wow, the maxrom itself will be a maxrom param. I think you can instantiate more than one, so I think we need to do map. Yes, we need to do a map. Case param. So it will create a the maxrom will be maxrom dot attach. About what? The params that we have, par, and the bus that we want to attach. In this case, I'm going to put it to the P bus. Perfect. Now we have it there. So instead of doing this, I am going to put in the RISC vector. I'm going to put it in whatever first maxrom we created. So I'm going to access the outer dot maxrom param dot of 0 of address.u. So it will reset there. And we are almost good to go. We need a base configuration that we can make before. So I like to use one one single configuration. So we are going to just use one single configuration, and I don't see where I can create it. RBC, I'm going to create it here. RBC config, Scala. Yep, something like that. Then again, I'm going to use the same RISC-V console system. I think we don't need about this, but we need the configuration chip from Chips Alliance, not the parameters, but the whole thing. And we need to create basically the same instruction as the core. So in order to do that, we are going to just copy it from the chipyard, just to have a stuff. Yeah, I know. You basically, what you need is to at least have one base configuration, so you can define all the variables that you need. But we are not going to do it like that. Well, we are going to do it like that, but we can personalize it. So for now, we are going to use one example. So the example will be obviously the rocket config. We have all of this, but we will modify it accordingly. So it will have the base config here, and the base config will configure this with the development port, the development MIO, the slave port, the time base, with DTS, with that bullshit, and the base system configuration. Finally, what else do we need to do? The basic system configuration will have the XLAN64. We need to see if we can modify this in another way that is not, because I wanted to do it in 32 bits with one tiny core. Can do it. Which one else can do it? With RB32. I think I will use with RB32. Where's my configuration? Here. Okay, we don't need the chipyard IO binders. We don't need anything about test chip. We don't need anything about chipyard. It includes cache with big cores. I mean, I don't want the big core, but I will have this. And we are not going to use coherent, we are going to use with incoherent, because it's just one core. This for avoiding use the Alt2 cache. We don't need Alt2 cache if you have only one core. That is overkill. No MMIO, no slave, includes cache, NB cores. Let me see if I can just NB cores, NMED cores, small cores, tiny core. We can use one tiny core maybe, because it will create the memory as well. Because we cancel this We create no MMIO, no slave port, nothing about this. The core will not have the stuff. So with tiny core, with arbitrary 2, I'm going to put this just for overkill. External interrupts, we don't have any. And we need here to actually not have the mem port, with no mem port. Thank you. This will not create no top level memory port at 800 at 80 million, because I am creating this here. And I think that is enough. Now we can finally create our stuff. Well, let's see. Let's copy this RBC config. Now we can finally make our final stuff on our final stuff. That is the harness. The harness will contain whatever the FPGA has, but for now we are going to just do the platform, because the platform comes first. So the platform, where's the platform? Blah 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 platform. I forgot where's my platform. I forgot where is it. It's here. New file. RBC platform. Scala. So this will be finally a file that actually will resemble what you are used to in Chisel, if you are worked with Chisel before. If not, shame for you. So class RBC platform that will extend a module, a plain module. We need to have an implicit p parameters. We need to have an IO. And your bundle here. And the bundle is here. We can finally have whatever you need here. So for example, the GPIOs and the stuff. So for the UART we need what is name it? An RX and a TX. That I know that they need to be optional if we are not going to include them, but stop nitpicking. The voice in my head, nitpick. URTX or TXD, I think it's named. Is a bool. Is an output bool. No, it's an input bool. We will decide it later. Maybe it's input output. I don't remember. RXD. This is the opposite. Needs to be input. For the GPIOs, we are going to create a vector of GPIOs. Is equal a vec of whatever GPIOs we created. Yes, we need to get that. P of periphery GPIO key. I think we need that inside of the sci-fi stuff here. We need also some another thing that the GPIO is going to use. That is the GPIO pin. The GPIO pin will be the GPIO pin gen. I forgot that this is a GPIO pin gen. I didn't remember that. And it will make the GPIO and will be port IO. The port IO is IOF pin with enhanced pin. This thing is what I need. So I need to include also this for the platform. But this pin control is the pin control. I mean, I will get the number of GPIOs here. So raw and GPIO is equals to the GPIO key dot of 0 dot the number of GPIOs that we need. There with it. So the number of GPIOs are here, and we need that every one of them is an enhanced pin. What is an enhanced pin, you ask? This is an invention from sci-fi that it has basically 6 signals that you can control a GPIO with. So it has the OVAL, the OE, IE, DS, PUE, and IVAL. You can put it as an output, you can put it as an input, and it will control a GPIO. It's just a GPIO is just a glorified three-state buffer. So that's why it has an open enable and input enable. You know the drill. You know the GPIO, how they work in a microcontroller. If you don't know, I suggest you to get in touch with Arduino. Okay, so we have up to here. So we have only our in our microcontroller the UART and the GPIO, and it's going to put a ROM inside of the ROM. That's literally it. It's a very bare bones, and we have 2 hours in this. This is not easy. So again, we need to instantiate the ROM, our stuff, the system. So in order to do this, the system will be the lazy model of the new this. But you also need the model. So this is the system lazy. As for the system itself, bound system will be the model of the system L.model. So as you can see, it will first create the lazy model, like create the whole parameter stuff. Then it will finally create the model when it is created. When you do it like this, remember that model is lazy, totally lazy. When you access like that, it will create the model in this moment. So that's why you cannot access the model before. Otherwise, it will create the model altogether. So we are here. Now we need to connect whatever mess we have. So, because we only care about the model and the lazy model, first of all, we are going to nullify the debug, for example. for each of this. I cannot tie off this thing. How do I tie off this? Because I don't want to debug. Ah, here it is. You can use this object debug. So it's not made in this way, actually. So you need to debug to tie off. We need to include this. So we have to need this thing. They have a whole utilities for this thing. We need to have this. What else do we need? The reset culture option, that is none. Option PTSD is no. We don't have any of that. So we are just going to put it down. Put it down, boys. Okay, that is for the debug. Now we need to connect the UART and the GPIO on whatever system they had. We are not going to use fancy reset systems, so there's that. And I'm not sure that you need to do something for connecting the resets and the clocks of each core, but I don't remember them. Probably is going to trigger in the FreeRTL, so we are going to expect that the FreeRTL take us to there. As for the other ones, so the GPIO will export the GPIO pins, if I am afraid. Yes, maybe. Yes, and it's named GPIO. So we can access the sys.gpio of 0 and get each one of this. Actually, we can do it like a for each. Yeah, I'm going to zip this one with the io.gpio. Hopefully it's okay. I think it's not. What is GPIO? The GPIO nodes.sit with index that makes the end.gpio, and then it will create this motherfucker. It's a sequence of GPIO port IO. It's a sequence of GPIO port IO. Wait, it doesn't flat them. What is the port IO about? Now I get it. It's the pins. This doesn't have this symbol here. Let's see if we can filter them. This is just for the sake of the idea to actually tell me what they are. Let me type a notation of this. That is not this actually. Is it's supposed to be a sequel. In the original one, it's supposed to be a sequence of GPIO port IO, but the thing doesn't know that, so we are going to do it like this. Yes, doesn't matter if this triggers, it's the same. But GPIO.pins, finally, okay. So it's good. So it's good this way. Case A, B, and we're going to connect together A and B. Kiss each other. Now we need to do the same for the UART. So the UART periphery will create the UART port IO, and the UART port IO, it has this, the TXT and the RXT. Pretty self-explanatory, no? So we need to do exactly the same for the other ones. We can do it like this. UART for the UART IO, and it will get me the UART. As for this, we need to import this. Everything about UART we need it here. This is the same. And now we need to connect those things. So io.uart txt will be connected to uart.txt, and the other way around for the other one. rxt goes to ioart.txt. Perfect. And we are ready. So it's not easy again. I am telling you, this is not easy. This is very stuffy. So right now, this is what we are going to put into the test harness. So we are going to put here the test harness. So the model will be this thing. The model package is not anymore this. We have RISC-V console.system. So this one, the config package is the same. The generator package is chibier still. The configuration will be whatever we put here. That is the RISC-V configuration here. The test bench and the top will be the system. Test bench, we don't have test bench. We leave it there. Okay, let's generate it again and see if we got it right. It's long enough. No, sorry, it's not this one. FPGA ULXC. So make default. And we will see finally it gets into the stuff. Out of bounds exception, because maybe we forgot to put it inside of the configuration actually. So sorry, my bad. So we need to put this periphery UART here. We need the UART here as well. So the GPIO and the UR, I hate when they do that. In the configuration, we're going to use this, and but we can just use it like this. Wait. Wait, how they do that? Okay. I need to create this thing. Class RBC fucking shit. RBC peripherals config extends this config of site here at of this. And we can just put it here near this. And now we need to put our stuff here. For example, case peripheral arch is equals to something that is a sequence of UR params. So sequence of UR params. Let's see what they take. Okay, I think I forgot to put the whole hierarchy stuff. I think I forgot to actually put it this thing. Perfect. Now we need to put this. It needs only the address for this one. So I'm going to put it in 60, maybe in the 10,000, 10 million. 10 million is okay. Don't know, don't care. Now the GPIO key. Now this GPIO. GPIO parents. So it needs to be a little apart. So I'm going to put it in this one. And it needs another one, no? It needs another stuff here. And a width, yes. We're going to put like 8 GPIOs for now. Okay, let's do it again. Now writing design, then created the GPIO and the UR. Wow, it looks good. Boom, died, but it almost got it. Okay, RB system. It out of bounds exception in RISC-V system 28 because I forgot to put the params of the boot ROM. So this thing I need it from here. Free chips of system, that thing. Case this thing dot preferring master on key is a sequence of of something. What is that something? It's a mushroom params, and the mushroom param needs the address and a name. Okay. The address will be obviously 10,000, and the name will be my bootrom. Also, this needs like this exposure here. Huh? Where is my mushrooms? Oh, okay. By the way, I'm going to put this a little distributed so it gets understandable better. Let's do it again. I need to do something about this simulator. The simulator projects. Woo! We have something. Wow. Look at it go. Now we create the top and the harness. So we'll first try to extract this one, and next the other one. Okay. So let's go right here. You know, it's difficult to debug this when you don't have any idea, but if you say the one flow is that I usually put this backwards. So we need to just clean and do it again until we have it. Come on, come on, come on. Samba, samba, samba. I'm cheering my code. If you make it. Come on, you can do it, you can do it. Come on, come on, come on. Yeah, yeah. Come on, give me green screen. Green o kudasai. Okay, it's like passing maybe. It's doing something. I don't know. Oh shit. Holy shit, it did it. No, I don't need it. Almost. We need to zero the clock DMI and the active ICK. And why? Why? Tell me reason. The only way to debug this is to actually mimic again what they did in the harness. There's not a way. But there's no way to know it. The chip top maybe has it. No. This hurts. This hurts my feelings. We can we can extract it from the rocket harness. Let's see if the rocket tells us something. C main Scala. I think that is system. Yes. It will connect to the back, but I don't want to connect to the back. I want to connect to the back. I want to what do I want to do? What do I want to do? What do I want to do? That is a good question. I don't know what I want to do. Okay, there's the connect to the back. Connect the back lock and reset, the back lock hardware, and the tie off the back. So according to the report, the stuff is that the clock DMI is not connected. Nothing about the DMI or the ACK or anything about it. That needs to go somewhere. So right now we have the debug module, but the other side of the debug module is totally unconnected, disconnected. We need to connect it somewhere, but for some reason, tie off the back doesn't help me with that. If the clock DMI exists, it will try to put the valid in 0, the ready in true, the DMI clock as clock, and the DMI reset as reset. That is not how it works. That is curious. Maybe sysl. Sysl.debug. No, it's sys.debug. Okay, let's tear it down. So according to the theory down of this thing, if it's a clock at DMI, it will connect to the clock at DMI. Yes. Connect the put clock and reset. Should I connect this with clock and reset first? What about tie off? What about debug? no idea. This is a little and it has same JTAG as well. No, I don't need any of that. What I need is to just make it go, like literally. But it doesn't detect the clock at DMI for some reason. Says the back clock DMI, and the ACK reset is 0 in that address specifically. Is the required bits, or the require is the operation? No, it's working. It doesn't 0 all of that. Do I need to do it? Manually? They don't have a function to do it for me? Really? I can't believe it. Yes, this will only put the clock and the reset to 0. Oh wow. They actually expect that at least the debug is on, and if you don't have it, they expect to connect the JTAG on top of. If I zero the JTAG, it will have it as a JTAG, and this won't be here because the JTAG will be connected to the DMI. There's no other way, but if we don't want to mess with this, we need to make it with JTAG. But that is a bug. You can see what you see there is a bug. So anyway, we cannot do it like this, but we need to activate the configuration for creating the system as a not as a DMI, but as a JTAG, and they have something like here for doing it, but I am not sure. With the bug SBA, with the bug DTM, with the bug I think it's with JTAG DTM. So we need to actually import it here. So whatever the crystal says. And I hate the indentation of this. Okay, already. I think that will be enough, but I'm not sure as well. Oh yeah, the reason why we clean is that we need to clean. We need to clean to actually get rid of the previous free RTL, because otherwise it already had the free RTL there and won't compile anything new about the notification that we do in the chisel. Okay, everything's good for now. Oh wow, almost there. We need to do something with that. Heart isn't reset. And the DM active ACK. So we need to see which one of the utilities of the debug will put the debug. Oh shit, there's two debugs here. Connect debug clock helper. Oh shit. I think we need to use this one. Let me see. They don't have it here, but we can use it. I mean, I don't see why not. That will do for that. Now we need to put the hearts in reset. We can just put it to the reset. I'm going to put it to the reset. Is this a or is this? This doesn't exist. Oh wow. I thought there was a... Wait, what is reset control? Reset control is an IO of reset I control IO. Okay, no idea. Is a reset control IO? What is inside of reset control IO? Okay, maybe we can do a for each here. Wait, reset control is an IO of reset control IO. Okay, and reset control IO, it has this bullshit. Yes? Yes. Wait. Is hearts isn't reset? Is hearts isn't reset. I don't get it. What is reset control? Reset control, what it is? I'm going to cheat it. I want to do a type annotation here. Yes, then why doesn't work with the for each? Okay. Ready. Now we have that. That was curious. And with that, I think we have everything done. Let's see. Wow, 3 hours doing this bullshit. I wonder why nobody does this. I mean, it's so practical to just use Verilog at this stage. I get the people that do it like that, but I also get that this is easier to implement systems with. I mean, all the configurability is actually priceless. That's what I like about this, actually. Wow, it passed. You are done. So generated SRC will have finally our stuff. This will have our hardware. So the harness will have the only the system, and the top will have the rest of the system. Sorry, the harness will have the platform, and the top will have the system itself. So we can see them. As you can see, this is just an instantiation, and the top model will be here. Look, the RISC-V platform, and we have the clock, the reset, and the UARTs that we have here. The reset system will be here, and the rest of the rest of the things are here. That is cool. We can export also the JTAG here and make it totally debuggable. I think we are going to do that in the next session. Then we have the top here, that it will have the whole system. The whole system is a very long system that actually only has one small core. But with the boys, there is no more teaching this lesson. So from here, it's about the next session. I think we will have to actually make it those ports that we did, to actually map it inside of this FPGA. We're going to do it using raw models. And yes, pretty much is it. I think we can have maybe a hello world running soon enough in the near future. So that will be neat. But beside that, that's all I have for now. We'll see what it will be to do the next one. The next one will be unknown territory for me, because it's about using that FPGA. So hope to see you there. Thank you if you were clinging with me the whole session. Really appreciate it. See you in the next week. Bye bye.